Hi everyone, I am Chaofan Lin from Stony Brook University. In this video, I'm going to talk about our recently developed resilient microgrid formation method with renewable integration. This method has been presented at the 23rd International Wind and Solar Integration Workshop held in October 2024 in Helsinki, Finland. And a paper has been included in the conference proceedings to be published. Our team for this paper has Professor Peng Zhang and Professor Yakov Shamash from Stony Brook University and Professor Zhongli Lin from University of Virginia. This work is supported by Office of Naval Research. I would like to thank all team members in this project for their help and contributions. This is an outline of today's talk. First, I would like to give a brief introduction about this work. In recent years, frequent natural disasters have significantly threatened the safety of electrical power systems. For instance, during the 2021 winter storm in Texas, over 4.5 million people lost power, with some outages lasted up to 4 days. Enhancing grid resilience has become crucial to minimize the impact of such extreme events and ensure a quick recovery. Microgrid formation is an effective strategy to enhance the resilience of distribution systems against extreme events. It involves dividing a larger system into smaller microgrids with flexible boundaries by controlling switches and the power outputs of distributed energy resources, or DERs. The importance of microgrid formation includes 3 key points. The first one is improved reliability. Splitting a distribution system into multiple microgrids enhances the reliability of local communities. The second one is fault prevention. Independent operation of microgrids prevents cascading failures and unnecessary inverter trips during extreme events. The third point is resource optimization. Microgrid formation maximizes the use of limited distributed energy resources to restore critical loads, significantly boosting system resilience. However, traditional microgrid formation faces 2 major challenges. The first challenge is that how to handle renewable uncertainty, which is the link between renewable energy variability and frequency and voltage excursions is often overlooked, leading to safety violations and instability. The second challenge is dynamic microgrid switching. The effects of switching actions on frequency, voltage, and other state variables are not addressed, making safe transitions between different microgrid configurations difficult. To tackle these challenges, we developed a new optimization approach for resilient microgrid formation. This ensures safe and reliable operation under both renewable power uncertainties and microgrid switching disturbances. We incorporate 2 new types of constraints. The first type is droop constraints. We use adjustable references signals to link renewable uncertainties with frequency and voltage changes. The second type is switching sequence constraints to ensure safe transitions between different microgrid configurations. Next, let's look at the details of the new formulation and methodology. The first set of constraints focuses on regulating frequency and voltage under uncertainty. We consider droop effects of grid-forming DERs. These constraints have three dimensions. The first dimension is S, which is scenario or uncertainty. The second dimension is I, which is spatial node. The third dimension is T, which is time evolution. The droop control references for each DER at each time slot are flexibly determined by the optimization process. The actual power outputs and the frequency and voltage variations under uncertainty are linearly related according to the droop equations. Additionally, the power output limits are included to ensure the safety of the grid-forming DERs. Next, we define the constraints for other sources, loads, and topology. Intermittent renewable power sources and uncertain loads are uncontrollable and introduce uncertainty when connected to the microgrid. To reduce this uncertainty, we can switch some of them off, though this will also lower the satisfied load or resilience level. The optimization process will determine the switch status. Additionally, we use a spanning tree model to ensure that each microgrid maintains a radial topology by changing the switch status of branches. Next, we define the system operation constraints, which include KCL constraints for nodal power, KVL constraints for branch voltage drop, microgrid frequency constraints to ensure all nodes in each microgrid share the same frequency, and security constraints including frequency, voltage, and branch power flow limits to ensure system safety under uncertainty throughout the microgrid formation process. Finally, let's look at the constraints for microgrid switching. These constraints are necessary because all actions in a microgrid switching procedure cannot happen simultaneously. For example, a typical sequence might be first branch switching, then load switching, followed by renewable power source switching, and finally grid-forming DER reference adjusting. To ensure safety during these transitions, we summarize the microgrid formation constraints for each time slot with equality constraints G and inequality constraints H. For the first step, branch switching, the branch status for the next time slot are included in the constraints set, forming new constraints for the transition to step 2. And step 2, load switching, the load status for the next time slot are added, forming new constraints for the transition to step 3. And for step 3, renewable power source switching, similar to the previous steps, new constraints are formed for the transition to step 4. And finally, for step 4, DER reference adjusting, this step naturally moves the optimization to the next time slot. For other switching sequences, the constraints for transitional states can be formulated similarly. After defining all constraints, we use the resilience-oriented objective function for optimizing microgrid formation. This function aims to maximize the restored load across 3 dimensions, which is uncertainty scenarios, nodes, and time slots, with corresponding weights. The overall algorithm for resilience microgrid formation with renewable integration can now be summarized. First, input parameters, including system parameters, forecast uncertainty scenarios for renewable sources and loads, and the optimization time window. Then we formulate and solve. We define the constraints and select an objective function, and then we solve the mixed integer linear programming problem using commercial solvers like Groovy. Finally, we output and implement. We generate the microgrid formation results, including branch, load, renewable connection statuses, and grid forming DR references. And all these control signals will be sent to the real system for implementation. Next, let's see how the method performed in a test system. The new formulation was tested on a modified IEEE 37-node test feeder, which was disconnected from the main grid due to an extreme event. The system includes 4 droop-controlled DRs for grid forming and 3 intermittent wind turbines. The optimization time window for microgrid formation is set to 4 hours, with decisions made every 1 hour. First, the optimization results show that the test feeder forms different microgrid structures for each of the 4 time slots. The 4 microgrids adjust their electrical boundaries over time. This flexibility maximizes the use of limited generation resources to support as many loads as possible during the blackout. Second, we define load served ratio, also LSR, to evaluate the resilience performance of the new method. We calculate LSRs for primary loads, secondary loads, tertiary loads, and all loads in a test system, denoted as LSR1, LSR2, LSR3, and LSRA. The data indicates that about 33% of loads are met during the blackout. This is an additional resilience benefit because this happens before the utilities start their restoration process. Next, let's look into the frequency and voltages in the system. We can see that frequency and voltages are always kept within safe ranges throughout the entire microgrid formation process. This confirms that the new formulation ensures safe transitions during microgrid switching. Now we compare our microgrid formation method with a deterministic one without uncertainty and a traditional one without considering switching constraints. Their methods seems to give much better optimization results. This is because our method do a careful search in a much narrowed feasible region, which reduces the optimal solution's objective value. We will show that even the other methods give good optimization results. They are actually infeasible and cannot be used in the field. The results show that the other 2 strategies lead to safety violations. The traditional formulation causes significantly more severe violations, about 10 times more than the deterministic formulation. The most severe violations happen on nodal voltage, followed by frequency. Therefore, neither the deterministic nor the traditional optimization can ensure system safety, especially regarding voltage and frequency. Let's take a further look. We can see that the traditional formulation can only keep the frequency and voltage variations within safe ranges for steady states, while variations during transitional states are uncontrolled and could lead to severe stability problems. The deterministic formulation may cause frequency and voltage variations in both steady state and transitional states. Finally, let's get some takeaways. We developed a new formulation for microgrid formation to enhance the resilience of power distribution systems during blackouts. It addresses challenges from renewable integration and microgrid switching. This formulation ensures system resilience by maximizing critical load restoration and guarantees safety throughout steady states and transitional states. In the future, we will explore more efficient algorithms to solve this formulation. This is the end of this talk. Thank you for watching. If you have any questions or comments, please feel free to send me emails. I would be more than happy to discuss with you.